Hello, my name is Seth Downs, and I'm pleased to be here due to the sponsorship of Positive Energy. We're here to talk about my remodeling of our home in Albuquerque to a zero-energy home. Hopefully you've tuned in. You may not know what a zero-energy home is, but if you don't, a zero-energy home is a house that can produce as much energy as it consumes on an annual basis. And in our case, we use solar electric or PV panels to produce the clean renewable energy. And once we figured that out, or once we had solar electric on there, we also were able to reduce our energy consumption by 70%. And we'll go into that in this presentation. Now, the story was started back in January 2009. My wife got a position here at the University of New Mexico as a professor. And we'd been looking all fall for a house. Not too much luck. And then come December, she calls me up while I was at work in Alaska, and she says, I found the perfect house. It doesn't have any heat. The water doesn't work. It's as is. And when I walked through it, I almost retched because it smelled so bad. And I said, perfect, honey. Let's get it. So we did. In January 2009, I walked into the house and started fixing the place up. Now, when we started this project, we didn't know what a zero-energy home was. We just knew we wanted to move in. And we had some idea about energy efficiency, but we didn't have any goals. And that kind of evolved over the years. And so we made a few mistakes as we went along. Some of the characteristics of the house, as I already told you, had no heat, no water. There was no insulation in the house. There was no southern exposure and too much western exposure. And what I'm talking about there is glazing or windows. You want windows on your south side, so in the wintertime when the sun is low on the horizon as it passes east to west, the sun comes in and warms your house. And then of course in the summertime it's high in the sky, and if you have proper overhang, then the sun will come in and heat your house. But however, you have a lot of western windows, that long western windows, western sun will heat your house in the hot summer, which is not very desirable here in Albuquerque. So we had the worst case scenario as far as windows were concerned. We also had a very leaky house. Had over 2,100 cubic feet of air leakage. So if you can imagine a hole in the side of your house about 21 inches by 10 inches wide, that is the cumulative leakage of our house. And you'll get air leaks, from your baseboard, from electrical outlets, sockets, lighting fixtures, ducts, things of that nature. In a word, this was the perfect remodel. And if you're going to do a energy efficient house, this is a great way to start. But like I said, we didn't really know what we were doing to start off with. So the first mistake I made was I put in a high efficiency forced air furnace. Now normally you'd think, well, that's a pretty good thing to do, right? But I later learned that if you put a ductwork outside your insulated envelope, you're pretty much giving away 30% of your energy to the outdoors. So my high efficiency furnace was instantly an energy hog. Now we're going to talk about the KISS principle, keep it simple, stupid. So all the things I've done in this house are mainstream. They can be serviced by most any contractor. And you can find them at most home improvement stores, or certainly online. So the 4 pillars of our net zero energy home, in order of importance, was to insulate and to seal all sides of the envelope. And I highlight the all because I'm talking about not just putting insulation in the attic or the crawl space, but also doing the walls. And air sealing is also very important. A consideration with air sealing is that we live in obviously an atmosphere, it's a pressure vessel. So if you focused on maybe the baseboard and the light fixtures in the ceiling, that'll give you the most bang for your buck. The next item was high efficiency mechanical systems. So your heating, your cooling, your hot water system. Next, you might want to concentrate on high efficiency appliances and lighting. So your refrigerator, your dishwasher, clothes washer, cooking stove, LED lighting, and low water fixtures. And I want to just talk about reduced phantom loads right now. Phantom loads are anything that's on all the time, so maybe a coffee maker with a clock in it. Also, a cable box is a notoriously large energy hog, TVs, garage door openers. So one way to tackle that is if you put like all your entertainment systems on a power strip. You can turn that off when you're not using it, and that'll save you some energy on an annual basis. Then the fourth thing, and that's last, is your solar electric, your PV, to offset your home's energy use. And one thing that's not listed on here, maybe the fifth pillar, it's kind of hidden, is you have to be a zero energy home family. There was an interesting case study done in New England. They built 8 zero energy homes and put in 8 different families, and they got 8 different results. Some were surplus energy, so they produced more energy than they consumed. Some were near net zero, and some were wildly over. So it pays to be conscientious in the house you live in. Okay, in this slide we're going to talk about insulation and sealing of your envelope. Our house was a cement block wall, which is pretty common here in Albuquerque. It's got a lot of mass to store energy, but has a very low R value, so it transfers heat rather easily. So before we did any computer modeling, and before I had any idea we wanted to be a net zero home, we'd already done a fair amount of work. So this is about 3 years into it. We put some insulation in the attic and the crawl space, and we put those numbers into the computer modeling. And I wanted to figure out how much insulation to put on the exterior walls and how much benefit air sealing would have on our house. So we found that if we added 1 inch of exterior foam with an R value of 6.5, we'd actually reduce our annual heating load by 40%, which is a pretty significant amount. If you doubled the insulation to R13, we got a reduced heating load down to 59. So you can see you have a declining value. As you add more insulation, you'll have less benefit from that. And so then it becomes a cost consideration. How much do I spend on insulation, and how much am I going to save on energy costs? And then you can kind of weigh that with how much energy will I get from installing a solar electric system. With the air leakage, something interesting happens with air leakage. If you reduce it by 500 CFM for my house, that's, imagine a 1 by 5 inches of holes being plugged in your house, you get a 9% reduction in heating. And that's a very linear thing. So if I reduce it by another 500 CFM, I'm going to get about another 9% reduction in heating. And I just read a blog on Green Building Advisors, and someone asked if I had a pot of money and I could put it towards more insulation or putting in really good air sealing. The expert said, definitely go with the air sealing. You'll get the most bang for your buck there. So I thought that was pretty interesting. This next piece, I'm going to talk about global warming potential of various types of foam that we put on the exterior of your brick house. Unfortunately, I didn't know about this as I was deciding what to do with my walls, but I read this and I thought I wanted to share it with you. So when I'm talking about global warming potential, GWP, think of 1 atom of carbon as 1. And if the global warming potential is 7, that's 7 times more detrimental to our atmosphere than an atom of carbon. Now the first one is ESPS, and this is the white beady board you'll find at your home improvement stores. It has an R value of 4, it's relatively inexpensive, it's easy to shape, and most of your local contractors are going to be familiar with this product. The next one down is XPS. This is the hard, rigid blue board you once again will find at your home improvement stores. It has an R value of 5, and it's not very environmentally friendly because it has a GWP of 1430. So it's pretty nasty stuff, and most energy efficient experts will recommend you avoiding it if at all possible. The next one, ISO, is the polyisocyanurate. This has a very high R value of 6.5 per inch. And with a GWP of only 7, it's quite environmentally friendly. And this is where I was really leaning towards. Unfortunately, it's fairly expensive, and most contractors aren't familiar with it. I was able to find one contractor here in Albuquerque that was willing to do it, but he had a problem with code and putting insulation, foam insulation over my chimney. And I definitely wanted to have that done because if you didn't insulate that, that's a huge thermal bridge allowing a lot of heat to escape from your house. So I kept on searching, and I ended up with polyurethane spray foam. The 2-pound high density is what you can put on your exterior of your brick house or block house. It also has an R value of 6.5. Unfortunately, the GWP is at 1030. But I found a contractor here in town that was very knowledgeable, and I thought had given me a good price. So we ended up going with that. Here's a HERS rating for our house, and this is a home energy rating system. That's what HERS means. It gives you a computer simulation of heating design load and energy usage through a year. And when you talk to HVAC contractors, they're rarely going to do a HERS or a manual J. They just do rule of hand, and invariably they're going to give you an oversized system probably. Another benefit of a HERS rating, they'll give you a blower door test so you can see where your air leakage is in your house, and you can mark it and go back to it later on and fix those air leaks. And it also gives you a much more accurate energy model. So the results below are based on my house with the R38 was already in the attic, R19 in the crawl space. I wanted to see what R13 on the walls, had R3.3 for windows, and 2100 CFM. So when they do a blower door test, what they do is they put their door into your doorway. It has a fan in it, and they depressurize it to 50 pascals. That's an equivalent of about a 20-mile-an-hour breeze. So our house had about 6.8 air changes per hour in those conditions. Now the first thing we'll look at is the annual load, and that's in millions of BTUs per year. And above that you'll see the abbreviations NG and DMS. NG stands for the natural gas high efficiency furnace that I already had in my house. DMS stands for ductless mini-split. These are air source heat pumps. They're very efficient. Think of them as a very fancy refrigerator. So the annual load means how much heat do I need to put in my house to be comfortable for the winter season. And you can tell them what temperature point you want. I told them I'd be 68 degrees is what we like inside. We're comfortable with that. And for our house, it would be 25.5 million BTUs to heat under natural gas, how much heat we need. For the ductless mini-split, 21.2. Now normally these numbers should be 2 because it's just how much energy do I need in the house. But once again, because my ducts are outside the insulated envelope, there's air leakage and loss of heat through the ducts, you're going to have a higher number for the natural gas. Now the number below, the annual consumption, also in millions of BTUs per year, shows how much energy I need to produce to create that annual load. Now for the natural gas, it's 29.2. Once again, due to the inefficiencies of having ducts outside your insulated envelope, we have a higher number. But something you notice interesting with the ductless mini-split, with these air source heat pumps, you have a much more efficient system. It only takes 6.8 million BTUs to create the annual load of 21.2. And they call that a COP, a coefficient of performance. So if I divide 21.2 by 6.8, that's going to be 3 something. So it's 3 times more efficient. Or let's put it this way. I can create, it's 1 unit of electricity, but I can create 3+ units of heat bringing into my house because it's bringing the heat from outside, literally, and putting it into your house. And you can do the opposite in the summertime. You can bring the cold from outdoors and actually bring it inside for you. And so how much is 6.8 million BTUs? And it says on the bottom there, that's equivalent of 68 therms, or just under 2,000 kilowatt hours. And this is, like I said, an annual consumption for heating our house. By the way, it's 1,600 square feet ranch. The next one is the design load, your right corner top there. And this is in thousands of BTUs per hour. And these are what contractors are going to determine what size heating system to put into your house. So you normally hear like a 1 ton or 2 ton. A ton is 12,000 BTUs per hour. So for the natural gas, I need 23.8, almost a 2-ton system. For the ductless mini-split, 16.1. So about, was that 1 1/3 ton system. So once again, you see it's more efficient. I'm going to step back a second. I forgot to talk about the cooling and the cooling under the annual load and the annual consumption. See how the annual load is 11.5, but the cooling is 2.0. So I have a COP of greater than 5. And the reason why that is because the delta T, the temperature from the indoors and outdoors. So in the wintertime, if you have a set point of, say, 70 degrees inside you want, and outside it's 30, that would be a delta T of 40 degrees. In the summertime, maybe it's 90 degrees outside and 70 inside. That's only a delta T of 20, and that's why you have a higher coefficient of performance in the summertime. And the last thing there, the energy costs, this is dollars per year. Even though the natural gas is widely inefficient, it actually comes in cheaper as an energy cost, $171 versus $215. And this is probably why natural gas is so prevalent in our nation. But one thing that doesn't consider is the cost for hookup. So in the summertime, I can't use natural gas to cool my house, at least not with my furnace, and what was that, $12 a month, say for 6 months. So all of a sudden it comes more expensive than going with my electric ductless mini-split system. Another consideration is that I can't make natural gas in my house, and nor do I want to, but I can make clean energy from solar PV. So this was really a no-brainer to go with a zero energy house, all electric. Next one is some slides of some of the installations we did. The works better in the attic. They turned on the blower before they had the hose up in the attic, so they filled my hallway up with insulation. We went with blown fiberglass. You can also go with blown cellulose. That's very good too, and maybe a little bit more environmentally friendly. It's also very cheap to put in there, and that's why you'll find higher R values usually in attics, not because heat doesn't rise, hot air rises. Heat goes from hot to cold, but you always find higher R values in attics generally because it's just cheap to put it up there, so why not put more in? The next one is the floor joists. We put 5.5 inches of spray foam in the bottom there, and these next 3 words, open cell, low density, and half-pound spray foam, are interchangeable, and contractors may use 1, 2, or all 3 of these to describe what they're putting in there. And that had about an R value of R19. When they say low density, it's very soft. You can get in there with your hands and rip it right out if you want to. And then up top, we put in 2 inches of the closed cell high density 2-pound spray foam that had an R value of R13. And you can see we just sprayed it right over the old stucco. And fortunately for us, we needed to replace the stucco anyways, so it was all kind of enveloped into the cost. And what they do is they just put the metal lath over that and they'll restucco it, and it looks really quite nice. And it's certainly more comfortable too in the wintertime. And next, my father-in-law, we started cutting out the old steel windows we had. They were single pane, they were pretty drafty, a lot of them didn't work. And we replaced them with a local company, Glassrite. They make double pane sliders here, vinyl sliders. And there's certainly better windows you can get. Fiberglass is more environmentally friendly. Triple pane is certainly much more energy efficient. But then you certainly have a much higher expense. And so you get back to the scale, right? You have to decide, well, how much am I going to spend on this particular energy efficiency item? How much is going to save me? And how much is going to cost for solar PV? And years past, 10 years ago, it was no question. Energy efficiency was the low-hanging fruit all the time, and you really want to make your house as energy efficient as possible. But with the steep reduction in cost of PV, there becomes a more intellectual debate as to when those 2 things balance. So for us, in this house, the double pane sliders were okay. Our house is all electric. We had obviously natural gas at one time, and I was thrilled to disconnect it a few summers back. Much to the concern of our HERS rater and HVAC contractor, the ductless mini splits and things like that are all kind of new in America, at least. Ductless mini splits have been around Asia and Europe for a long time, but they're just starting to get to more mainstream here in the U.S. And they're very common now for zero energy homes that are being built from scratch. They're very popular. Like I said, they're very quiet, they're very efficient, and we'll get into those just a little bit more. The next one down is induction stove. It's also super efficient. And in the bottom there, I mentioned he monitors energy use. So this is Mark Rosenbaum. He's a double graduate from MIT. He was actually a teacher of mine. I took an online course, 10-week course on zero energy home design. And the capstone project was to design a zero energy home in wherever you wanted to. And I designed one for Anchorage, Alaska. And so that was really empowering to learn how to design an energy model and determine the mechanical and appliances for a zero energy home. And if you can do it in Alaska, you can probably do it almost anywhere with the right site location. But anyways, Mark has this blog called Thriving on Low Carbon, and he moved into a house that he also turned into a zero-energy home. And along the way, he describes all his rationale. He also energy monitored each system before he changed them out, and then compared it with the new system, so you can see how much efficiency he gained. And with the induction stove, compared to his natural gas, he found it 77% more efficient, or at least 77% less energy than gas did. What it does is electromagnetic. It excites the molecules right in the pan. And so you'll have very even heating. It'll also be very fast, so you can boil water in like 90 seconds. It's also very accurate. You can set the temperature to any level you want, and we love cooking on it. You can also get, if you can't replace your whole stove, you can also get little hot pot tabletop ones, which we have in Alaska. We use that. You bought it at Costco for $30-40. And I find I use that probably 90% of the time for my cooking, because I just enjoy using it so much. Another benefit of an all-electric house is there's no combustion. I'm not burning fossil fuels in my house. I don't have to worry about gas leaks. And finally, it's easy to monitor energy use. You know, you look out, you can track down what your meter reads one day or 1 year and come back and look at it again and see if it's spinning forward or backwards, and you'll know how you're doing. Okay, next we'll talk about the high-efficiency appliances. Those two websites listed there, the ce.1.org and Top 10, will list your high-efficiency appliances for you, and it's a much better guide than you'll get from the Energy Stars. CE1 is very detailed. They'll break it down by model numbers and the different energy aspects of each appliance. Top 10 USA is kind of a fun site to go to. It's easy to use, and it'll give you the top 10 most efficient appliance for each thing. And also they'll compare the cost of the appliance and how much energy you'll use for that particular appliance over a certain period of time, and give you like a total cost, so you can compare apples to apples. So we'll talk about each appliance listed here. The Marathon electric hot water heater. So this is a hot water storage unit. It has a plastic liner instead of a metal, so it's going to last longer. It's not going to rust out. And then they put spray foam around the outside, so it's very efficient. And electric hot water heaters are actually more efficient than gas, because they don't have, gas has that flue in the middle, right? So the hot air is always escaping through the top. But people go with natural gas just because it's very cheap to get natural gas. Next down is the front load clothes washers. Those are becoming more and more common over the last decade or so. They're very, very energy efficient. They use less water. They can spin your clothes at a higher speed, so when you put those clothes in the dryer, it'll be less energy to dry those clothes. And also they're much more gentler on your clothes, so they'll be good for your clothes as well. For us, we don't use a dryer. We have a clothes rack you can see in the back there. We also have a clothesline, or you can use your shower rod for maybe your sheets. And in Alaska, we almost never use our dryer. We just do what I said. Like I said, we use the shower rod for the big stuff and have a clothes dryer, and it works great. Next, the refrigerator. And there's a few things to consider there. The freezer on top is more efficient. A smaller refrigerator is more efficient than a large refrigerator. A full refrigerator has more stuff in it, has more mass. It's going to be more efficient than an empty one. Obviously, things like ice makers and water makers on the side of the door, definitely a no-no. What's really interesting, if you look at the Energy Star guide, they don't consider having an ice maker in there. And so an ice maker, I didn't realize this until I read Mark's blog, to get the ice out, they actually heat the mold. So you have a heater inside your freezer, which is pretty crazy. And then it's even crazier that they don't consider that as part of your energy use for the annual consumption. And so they did a study, and they figured about 12 to 20% increase in your energy consumption for your ice maker. And the last one is your dishwasher. You go to Top 10, you'll find lots of dishwashers that are energy efficient now, and it'll make a big difference. Use less water, generally speaking, than washing your dishes by hand, unless you're wildly efficient hand washing. Okay. Now, a lot of people, we're going to talk about hot water again. Mark Rosenbaum has an excellent 4-blog series on it, and I recommend you read that. So throughout the slideshow, I have hyperlinks. And at the end of the slideshow, I have my email or phone number if you want that, or maybe it'll be on the web page. You can get access to this slideshow, and then you can have access to these hyperlinks and follow up with more research on your own if you like. But some key points for hot water is to minimize your distance from your hot water tank to the fixtures in your home. Try to centralize that. Using smaller diameter piping, and obviously to reduce your usage with low flow water fixtures and energy efficient appliances. Okay, and then considerations, what kind of hot water system do I want? And the list there is determined from low usage to high usage. So this might come as a surprise to some people that Mark recommends a standalone insulated hot water storage heater, like I recommended with the Marathon, because it's energy efficient, but also it's just simple. You can find this in stores. Any plumber can fix this, and that's why he went with that. And with PV price coming down so much, you can have the sun heat your electric hot water heater for you, and it just makes sense. And that's the way a lot of zero energy homes are going now. Now, if you have a bigger house or you want to try an air source heat pump, it's similar to a ductless mini-split, same principle, but there are considerations with that. Because it's extracting heat from the air, if you have it inside your house, that room it's in has to be fairly large, like say 10 by 10 feet at least, and it's going to be cool, which might be nice in the summertime, but not as nice in the wintertime. So you may not want it to be in a space that you're in quite often. Also, it's going to make more noise. It has a higher decibel rating, so having it close to a living space might be uncomfortable in that regard. So maybe in the basement or at a large closet out of the way, or in your garage might be a place to put that. And then last, the solar hot water heating. If you're using a lot of water, maybe a really large family or something like that, you might want to consider solar hot water. Because it is a fairly complex system, the prices haven't dropped as much as the PVs have. And that's why I think Mark brings it down to the bottom a little bit. Kind of back to the KISS principle. Other efficiency items, I recommend the Niagara 1.5 gallon per minute shower heads. The code right now is 2.5 gallons per minute. We tried different shower heads, from different high price ranges to lower price range. We tried the 1 gallon, the 1.25 gallons, and for us, really 1.5 is about as low as we go and still feel comfortable. This shower head pictured there is about $15, so it's pretty reasonable considering you can spend $50 to $80 for other low flow shower heads. A low flush toilet, we have a 1.28 gallon per flush. The code now is 1.6. And if you have a toilet that's 10, 15 years old, that could be consuming somewhere between 3 and 5 gallons per flush. And I know for us, the utility actually gave us money to replace that toilet. So it was actually free for us. So that was an easy decision. And in fact, if you saw the pictures of the toilet when we moved into the house, you'd know why I replaced those toilets. I had to spend an hour cleaning it so I could rip it out. It was that gross. LED lighting is getting better and cheaper every month. And as opposed to CFLs, it has no mercury and it actually lasts a very long time. They said the same thing about CFLs, but I've been having a problem with those for almost 2 decades now. I'm always kind of burning out. But I have had LEDs for 10 years. I've never had one fail. I've dropped them. They're rock solid. Like I said, they're getting cheaper and they're super energy efficient. And some complaints are that they don't like the blue light of LED lighting. So if you look at the back, they'll talk about kelvins. So you want 2700 kelvins. That'll give you the same color as an incandescent bulb. And you might be able to go up to 3000. Getting higher than that, you're going to start getting the bluish light, which some people don't like. But yeah, just go to your home improvement stores, and Lowe's and Home Depots, they'll have different brands, and see what you like and see what it fits. We pretty much have LEDs throughout our entire house now, and they're wonderful. And we've talked about air sealing your house. Obviously, if you make your house a balloon, super airtight, you're going to have to bring in some mechanical ventilation. And the gold standard, especially if you're going to build a new house, would be to bring in mechanical ventilation with an energy recovery unit. So you transfer the heat from the outdoors to the indoors, vice versa, depending on the season. We didn't go with that option. We went probably with the next thing down. This is a little, maybe a little energy intensive, or you have to be a conscientious owner. So this is a whole house fan, and it's sort of like a backwards swamp cooler. So what it does is I'll open the windows on the far corners or the 4 corners of the house, and I'll turn on the fan, and that will suck hot air up through the ceiling into my attic, and then from the attic it will vent out to the outdoors. So this is great on cool summer nights, or maybe on the shoulder season like spring and fall when it's cool at night but warm in the daytime. I want to bring some heat in. I just crack that window open, turn on the fan, and it's very energy efficient. So you can see those are the fan speeds, 25 and 1500 CFM. So at 1500 CFM, it only consumes 44 watts, and it's fairly quiet at 37 decibels. And I'll use this in the wintertime as well. Because I have all that mass from the block walls, I'll just open those windows, turn it on for like 10 minutes. I've totally changed the air in my house, and I'll close it up, and my house will warm right back up again as the heat escapes from the walls. And then probably the last thing you could do for bringing fresh air into your house would be using high efficiency bathroom fans with a timer. You want to get like a DC, a brushless motor. They're very efficient, low energy use, and you put it on timer so it actually will bring in fresh air at a planned amount at certain hours of the day. So if you seal your house, you definitely need to consider how you're going to bring fresh air into there. Now this is the layout of our home. Like I said, it's 1,600 square feet. These ductless mini splits, we go back to that HERS rating, I needed what, 16,000 BTUs per hour. The smallest system they make is 9,000 BTUs. And you can have one outdoor unit and multiple heads indoors, or in our case, we used one outdoor and one indoors. Consideration is you only go about 40 feet from your outdoor unit to the indoor heads. And if you have a well-insulated house, you can get away with less ductless mini splits. If you don't, then you're going to need more heads inside, because these are point source heating and cooling, right? So you can see it's in the far living room. It has to heat all the way into the kitchen and laundry room. And so on a hot summer day, if you're cooking pizza, you have family over, or if you're opening that door a lot of it, it's going to get warm in the kitchen. And so it'll get to be about 5 degrees of Fahrenheit difference between the living room and the kitchen on those days. So when you place the locale of your ductless mini split, consider how you use your house, where are your heat sources, what doors you're using, at what time of the year. So this is a ductless mini split. The top unit is on and operational. You can see the hatch is kind of laid open. You can see the black strip in the bottom. And that's the fan. The bottom picture is the outdoor unit. And these things are really fancy. They have remote control with motion sensors, time of day usage. You can change the speed of your fan. You can put it on automatic. It's variable speed, very quiet, very efficient, and highly recommend them. The energy guide here, so they have a scale from like 10.9 up to 21, and for mine it's 27.2. This is the SEER, this is like the cooling rating. So it's off the chart, super efficient. And like I said, I have one outdoor unit to one indoor unit. And like I said, you can put more units off that, you're going to get a little bit less efficiency, but your cost per unit is going to certainly go down. That unit there is about $3,000 right there. So the final step for us to getting net zero was installing some solar PV. We put in some sun power panels. Positive Energy installed them for us about 2.5 years ago. And our 3.84 kilowatt system produced about 7,300 kilowatt hours. So actually produced that much, resulting in about 1,900 kilowatt hours per installed kilowatt, which is obviously, as you know, there's lots of sun in New Mexico, and we do it great here. I think most installers now, they'll say, we can guarantee about 1,800 kilowatt hours per installed kilowatt. And the cost right now, I just asked them, is about $4,500 per kilowatt. So you can use those numbers to create an estimation of how much energy you can produce, and then you can start figuring out your efficiency goals and costs from that. Right here, we have our house, our solar panels on a pergola. They're going to be much cheaper and generally preferable just to put them on your roof. But like with our glazing, our south glazing, we had lots of shade on the south side and weird roof angles, so it wasn't an option for us. Unfortunately, we did have a good backyard, and so we built this pergola, and now we enjoy barbecues and whatnot out there underneath our PVs. Now this is a slide, and this will bring home some of the things I talked about. The peak daily energy use dropped from 64 to 31 kilowatt hours, which is a 71% reduction. Now the red line is our energy consumption over the different winters. The first peak is we moved in about April, and then that first winter we had the forced the high efficiency gas forced air furnace. Hadn't done any insulation. We had some efficiency items in there, like the refrigerator and the dishwasher, and I think the clothes washer, but that's about it. And that consumed 64 kilowatt hours per day on the coldest month. The next winter, we got some insulation in the attic and in the crawl space, had the new windows installed, and we put some new doors in there. And that dropped it a little over 10%, down to 44 kilowatt hours per day. Now this next winter, you see a huge drop. And this is where I talk about doing all sides, right, of insulating your house. So by this time, we got the R13 exterior walls on, and it dropped by over 50% our energy consumption, down to 67 kilowatt hours per day. And the next one you see the ductless mini-split heating, dropped it another 50+%, down to 31 kilowatt hours per day on the coldest month. And then if you go further along, you see it spike up again. And this goes back to the fifth pillar. You have to be an energy conscious household. My wife and I were on maternity leave in Alaska, and we rented the place out, and we had a family of 3 living there. Obviously, they have a different consideration of what their comfort level is, so we have more energy use. The green line just depicts the kilowatts produced by our system, and the blue line is the difference between consumption and production. So if the blue line is below the 0 line, that means we had energy surplus, and then if it's above, it means we're consuming energy from the grid. Right now we have about 4,000 kilowatt hours credit with P&M because we're a surplus energy house. Here's a slide on our costs, about $40K to do our energy improvement on our house. Like I said, R38, I talked about it, was cheap, so it was about $800. And at the time, there's a rebate from the utility company to put some of that in there. The R19 spray foam, that's about $2,500 in the crawl space. The R13 gets a little more expensive. That was about $5,900, probably a little more square footage than the other places. But as you saw, that made a huge difference in our energy consumption by putting those 2 inches of foam on there. It also makes the house a lot more comfortable in the wintertime. Extra charge for high efficiency appliances, about $1,500. And I think you'll find the induction stove really being the large chunk of that one. Double pane, low E windows throughout the house was $4,500. The foam core doors, about $1,000. The ductless mini split, $5,700 for those 2 units, which is pretty much what it cost me to put the natural gas furnace in there. Too bad I didn't know about it beforehand. Oh well. The whole house fan was $1,500. And lastly is the PV system, about $17,000 after rebates. And like I said, if you put this on your roof, and with the price reductions coming down so much over the last few years, you're going to find that probably half the price what I paid for it. So some of my resources where I've learned a lot is Thriving on Low Carbons. That's Mark Rosenbaum's blog. Green Building Advisors, put stuff on there almost every day. It's just a great resource. If you want to read a book, Ed Meinster's book on energy-free homes for a small planet is very good. And here's a check from P&M. They pay me now on a monthly basis, and I get about $500 a month, or $500 a year from them. Another resource is 1,000 Home Challenge. They're documenting and verifying existing homes that have reduced their energy consumption by 70%. And you can go there and you can see all these case studies and learn a few things, and you'll find our house on there as well. And that's where we got the idea of reducing our energy consumption by 70% was through the 1,000 Home Challenge, and we just barely made it. This is a fun slide I just made, and compares consumption and costs. So our house consumes, this slide got mixed up a little bit. So my house consumes about 6,400 kilowatt hours per year. Now you compare that with your average car. If you're driving 12,000 miles, you have a car that does about 30 miles per gallon, that consumes over 16,000 kilowatt hours. So almost like 2.5 times what your house consumes. So cars are really energy hogs. Now if you had an electric car and if you drove 12,000 miles, you get about 3 miles per kilowatt hour. That's only about 6,400 kilowatt hours. So electric cars are really the way of the future. And so I got excited. I said, wow, this is pretty cool. For only 6,400 kilowatt hours, I can drive my car. And I said, well, how can I do this? I said, okay, if I put in 2.1 kilowatt unit, it's going to cost me this much, and the rebate's about $5,400. All of a sudden now, for $5,400, I have a gas station powered by the sun that's going to power my car for the next 25 years. And the link, This is the Future, just goes to an article by a bank in Switzerland, a USB bank, saying how fossil fuel power plants are going the way of the dinosaur. That with the reduction in PV, wind, and the future of battery technology and the cost coming down in that fossil fuel plants will be going the way of the dinosaur, which is pretty exciting. So if you have any questions, please feel free to email me or call me. Like I said, if you need access to the hyperlinks, by all means, send me a link. I'd be happy to answer your questions. Thank you.